All right, welcome to 5.2. We're going to be talking about ANOVA testing. And ANOVA is short for analysis of variance. So it's still hypothesis testing. However, our groups are going to be our formula is going to be a little bit different, and our groups are increasing. So typically we can do a single sample test, which we did in chapter 4, a paired test, which we did with one population, but it was a dependent test. And then we've been studying independent tests with 2 populations. Now, what happens when we increase our sample groups and we have more than 2? That's when ANOVA testing comes into play. So it's a hypothesis test used for more than 2 groups, and it compares the variance within groups to the variance between groups. So important here, variance, remember, variance is spread, or you can think about it as standard deviation, but it's the distance within the group. So here's 2 words that we want to talk about. Within is variations caused by differences in individual groups. So first of all, there's another distribution back here that we can't see. So you can tell here that we have 3 different groups that we're comparing. So ANOVA allows us to test whether there's a significant difference between and within these 3 groups. So we're taking ratios of the groups and comparing those. So here's definition of within the group is the variation within each individual group itself. So I want to know standard deviation of the 3 groups that I have here. So let's say that I want to know if there's a significant difference between, between Coke and Fanta, or the caffeine effects of Coke, Fanta, and root beer. I can compare those using ANOVA testing. So here's between. I'm also using the between. It compares the variations of each group to the others. So you can see here the variation here. I'm looking at the variation between each group. So the grand mean here is another word that we're going to be discovering, is the average of all the data points in a set. So let's say that I had 500 volunteers come, or a sample of 500 people come and do a caffeine test with all 3 different sodas, Fanta, Coke, and root beer. The average would be finding the caffeine effect of all 500 and then dividing it by the total number that were in my sample, which was 500. Regardless of which group they belong to. It's also known as the pooled mean or the overall mean. We'll be using grand mean and on-ramps. And then here's our final word that I want to discuss is F statistic. An F statistic, known as an F ratio, remember we're finding the ratio of between variances and variances within, measures the ratio of 2 variances and indicates whether the differences between the groups are statistically significant. So instead of using a T statistic, we're using an F statistic because we have to use a different critical value. We're not going to be using the T table anymore. We're going to be using an F table to determine what that F critical value is, because we have different types of degrees of freedom here. So let's go down to our formula, which is a little bit hefty, but here's our between and within. So we're calculating a few different things, and in on-ramps we won't really have to calculate the sum of squares, but here's the formula for sum of squares between. And then degrees of freedom between. So notice we have a new variable here, K. K equals the number of groups. So going back to our Coke analogy, or Coke, Fanta, root beer, effects of caffeine, there were 3 groups, right? Coke, Fanta, and root beer, the effects of those 3 caffeinated drinks. So the K value here would be 3. And then we have within, so here's our sum of squares within. And then we have N minus K calculates our degrees of freedom for within. So K, again, was the number of groups that we had. N was the total sample size. So 500, right? If I had 500 samples for the effects of caffeine and K was 3, then my degrees of freedom would be 500 minus 3, so 497 would be my degrees of freedom for within. Now for the total, it's my degrees of freedom, or my total sample size minus 1. So for the Coke analogy, it would be 500 minus 1. Your mean squared is your sum of squares between, so whatever is calculated here, divided by the degrees of freedom between, K minus 1. And then your mean square for within is your sum of squares for within divided by your degrees of freedom for within. And then that finally gets us to our F statistic, where it's your mean square between divided by your mean square within. So I want to put something on here because this is going to help us determine our F critical value. Your degrees of freedom, these are going to tell you what our F critical values are. So I'm going to put this on here. I know you don't know what it is yet. This is going to be your wait, is it? Yeah, numerator. And this is going to be your denominator. And we'll do this in class when we get back together. All right. Our hypothesis testing steps are going to be the same, just like our t-tests, where we are stating our null and alternative hypothesis. In this case, our null hypothesis is we're stating that the population means of all groups are equal. So that would be mu1 equals mu2 equals mu3 equals however many groups that we have. The alternative hypothesis would be stating that the population of all groups are not equal, or at least two means differ. So thinking about our Coke analogy, that would mean that the caffeine effects of Coke would equal the caffeine effects of Fanta, would equal the caffeine effects of root beer. Now, or would not equal, sorry, that would be your alternative hypothesis. Another match for the alternative hypothesis is stating that two of the groups don't match. So it could either be 1 and 2, or Coke and Fanta, or Fanta and root beer. The kind of hitch of ANOVA testing is that it doesn't tell us which is true. It just tells us that something is not equal, right? So either they're all three not equal to each other, or that two of the groups are not equal to each other. All right, so our significance level is the same, 0.05, and here are our assumptions. We're assuming that we have random samples. We also have independent observations. Our distribution of each group is normal, just like we saw on that front page, that picture, and the variance of each group are approximately the same. And then our third step is analyze the data and compute the test statistic. So between is K minus 1. Again, K is the number of groups minus 1. Within is N minus K. Again, total sample size minus the number of groups. And then our test statistic, F, is the ratio of the between the groups mean squared divided by within the groups mean squared. Excuse me. All right, and then fourth, the most important part is interpreting the results. Do we fail to reject, or do we reject? Remember, fail to reject is stating that we did not observe any evidence that suggests that they don't have a different mean. So the mean differences in 0 is probable. And then rejecting the null hypothesis states that there is a difference in the means, whether it's the difference between all three means or it's a difference in two of the means. So here's a couple of examples I wanted to share with you. So your independent variable is social media use, and you assign groups to low, medium, and high levels of your social media use. Your independent variable is brand of soda, and you collect Coke, Pepsi, Sprite, and Fanta to find out if there's a difference in price. So there's 3 groups here, 4 groups. And then here your independent variable is a type of fertilizer, and you treat crop fields with a mixture of 1, 2, and 3. So just like we were comparing juniors and seniors GPA, we can now compare freshman, sophomore, junior, and senior GPA to see if there's a difference in those groups. Well, let's try this out as an example calculation before we move on. So you'll see something like this probably in your homework, and give you a second to look at it for numbers. So there it is. All right, so let's go and look at our first column here, the sum of squares. So usually these values are going to be given to you. So between is 100 and within is 301. The total is our sum of squares added together. So 100 plus 301 gives us 401. So our sum of squares is 401. All right, degrees of freedom. Remember, between was k minus 1. So we can work backwards to determine what k equals. If k minus 1 equals 2, then k equals 3. All right, and moving down here to the total, we know that our degrees of freedom, should probably reference our formula chart, right? Our degrees of freedom within is n minus k, and n represents our total. Nope, we wanted to look at the third one. Our total degrees of freedom is n minus 1. So if our total degrees of freedom here is 45, and n minus 1 equals 45, then we can determine that n equals 46. Now looking at within, our degrees of freedom here are n minus k. So we know the n value, and we know the k value. That's 46 minus 3, and 46 minus 3 is 43. So you can kind of see as well, 2 plus 43 also equals 45. So we could have subtracted and found that out, but I wanted us to look at the formulas in there. All right, so the mean square for between, let's go back and look. The mean square for between is the sum of squared between divided by the degrees of freedom. So my sum of squared was 100, and our degrees of freedom were 2. So 100 divided by 2 is 50. So our mean square for between is 50. Now our within is our sum of squared from within divided by the degrees of freedom for within. So 301 divided by 43, and that equals 7. So looking at our F statistic, we're moving forward. Our F statistic is our mean square between divided by our mean square within. Why? Because we're comparing the variances of between to within, right? And that takes a ratio. So when we compare, we're using that ratio. So mean square between was 50, and mean squared within is 7. And so our solution here is 7.143. So finding our F critical value is going to take a different table, and I'm just going to go ahead and tell you what it is this time, and then I'll introduce you to the table when you get back. And our F critical value is here, 3.32. Now, it helps to know, or that they gave us the p-value, because we know that our alpha level was 0.05. And if they gave us a p-value of 0.002, our p-value is less than our alpha level. So we know that we should be in the critical region, we should be in our reject region, but let's do our distribution just to make sure. So here I have 0, and then I'm putting my critical values here and here, 3.32 and negative 3.32. And my F statistic is 7.143. Well, that's way out here. So this helps me to confirm that I'm in the reject region, I'm in the critical region here. And so I need to reject my null hypothesis. So I am stating that there is a difference there is a difference in means. We don't know what the means were or what we were testing for, but we know that there is a difference. So knowing that the p-value is 0.002 and it's less than the alpha level, I know that this has been confusing some of you, especially on the quiz. The p-value is less than the alpha level, then it's in the reject region, because this is the probability that we'll see the sample size in the population, right? So there's a very low probability that it is part of the population, 0.002, which is 0.2%, very, very low, which helps us to confirm here 7.143 is very far from 3.32. It's way more extreme. So we do have evidence to suggest there is a difference. Now we will do some more of these in class, and we'll practice using that F table when you get back.